Hi, this is Dr. Collins Jones again, and this is segment 3 of my quick review of Solution and Dilution Lab Math video series. In this segment, we're going to discuss dilutions. We're going to discuss what a dilution is, how to calculate dilution values, what dilution factors are and how to work with those, and how to prepare a working solution from a stock solution. Let's get started by just considering what a dilution is. And on this slide, we're really just going to kind of do this intuitively, sort of think it through, but for the rest of this segment, we're actually going to formalize how we do dilution calculations by using dilution equations. So first, a dilution is accomplished by adding more solvent to a solution and increasing the volume. So we're going to increase the volume that our current solution is in, or we're going to add concentrated solution to a larger volume. But no matter how you think about it, the solute molecules are going to be more spread out. They're going to be fewer solute molecules per unit volume. Okay, so we're not changing the amount of solute, we're just changing the amount of solvent, the volume that the solute is dispersed in. The solvent that we are diluting with is often referred to as the diluent. So the diluent is the liquid in this case, and in our case it will be ultra-pure water because we're concerned mostly with aqueous solutions. So the diluent will be ultra-pure water. This is what we're going to use to dilute with. So let's work our way sort of as a thought process through a dilution example. And here we're saying dilute 1.00 liters of a 12.0 molar solution to a final volume of 2.0 liters. So here's how we think about this. We're talking about molarity, and molarity is 12.0 moles per 1 liter. That's what gives us the 12 molar solution. So if we look at this as an image, here we have a 1 liter volume, right? That's what the cylinder represents, a 1 liter volume. And in that 1 liter of volume, there are 12 moles of solute, each mole represented by a diamond. And remember, each of these diamonds is 6.022 times 10 to the 23rd molecules, right? So 12 moles and 1 liter gives us a 12 molar solution. But what we're asking here is to add another liter of solvent, another liter of diluent, to give us a final volume of 2 liters, right? 1 liter plus 1 liter is 2 liters, so the volume has doubled, but we still only have 12 moles of solute in here. So if we put that information into our molarity equation, it's going to be 12 moles of solute per 2 liters of volume. And if we simplify this, divide 2 into 12, this becomes 6 moles of solute per 1 liter, or a 6 molar solution. And just over here on the left, I've just sort of put that into an equation form without all the images, right? And so essentially we have, after we consider the new volume, we've doubled the volume, so we've decreased the concentration by half. We've doubled the volume and we've decreased the concentration by half, okay? So you can think your way through this problem, but there's a better way to do this. And so typically in the lab, most people do dilution calculations using the formula C1V1 equals C2V2, right? And if you've had chemistry, you may have seen one version of this formula, and that would be M1V1 equals M2V2. So this is dilutions for molar solutions. M1V1 equals M2V2. But this way of expressing the formula as C1V1 equals C2V2 is more universal, because really we can dilute any units of concentration. So this equation allows us to calculate the dilution for any unit of concentration. So let's look at what these mean. C1 is the initial concentration, the starting concentration. It is the larger concentration in the problem. So if you have two concentrations, the bigger value is going to be C1. This is the concentration that you are starting with. You are using the concentration of C1 to prepare a more dilute solution. C1 is also the concentration of the stock solution. So it's the bigger number. You just compare the two concentration values and say which is bigger. The bigger one is C1. V1 is the initial volume. It's the smaller volume of the two volumes. It's the starting volume. It's the volume that you're going to begin with. So it's the volume of C1. So V1 and C1 are sort of coupled to one another somehow in the language of the problem. C2 is the final concentration. This will be the smaller concentration. This will be the concentration you want to end up with. This would be the concentration of the working solution. Okay, so this is the concentration, again, you want to prepare. And V2 is the final volume. So this is going to be the bigger volume because we're spreading out the solute, right? So this is going to be a larger volume, a bigger number compared to V1. It's the volume of the solution that you are trying to prepare. Okay, now I said that C1 V1 equals C2 V2 applies to any units of concentration, but there is a caveat to that, right? There is a catch. And so the catch is C1 and C2 must be exactly the same unit of concentration. Doesn't matter what that unit is, but C1 and C2 must be the same unit. So C1 and C2 must both be molarity, or they must both be percent weight volume, or percent volume. But they must be the same unit of concentration. So if C1 is given to you in molarity and C2 is given to you as a percent, then you must convert one unit of concentration into the other unit of concentration so that they're both the same. Similarly, V1 and V2 must be exactly the same unit of volume. So they both have to be in liters, or both in milliliters, or both in microliters. If one is in liters and the other is in milliliters, you need to convert them both to a same common unit. Finally, you must know 3 of the 4 values in the C1 V1 equals C2 V2 equation to complete the calculation. Okay? And that also, and we'll illustrate this in the worked out examples coming up, that also tells you this is a C1 V1 equals C2 V2 problem if you have 3 of these variables given to you in the problem and you need to determine the third. So let's start here. Let's just get started by working some examples. Determine the volume required to prepare 625 mils of a 4.25% solution. The stock solution is 25.0%. So if you remember from segment 2, the pattern of steps I gave you about how to solve these problems. First thing is read the problem carefully, look at the words so you can match the numbers to what you need to do. So we need to prepare 625 mils of this percentage solution, right? And then the stock solution is 25.0%. So I always start these problems by writing down the main equation. Right? This sort of helps anchor you. It gets you oriented. So we're just going to write down C1 V1 equals C2 V2. The idea here is not to take any shortcuts. The fewer shortcuts you take, the less mistakes you make, and the better that is for your grade or for your company. So we've established that this is a C1 V1 equals C2 V2 type of problem. So now we need to identify what number goes with what variable. So what is C1? What is V1? What is C2? What is V2? So again, this comes from reading the problem. Okay? So volume required to prepare. Right? So if we're preparing something, we're ending up with it. So that must mean that this is going to be an initial volume or a starting volume. This is a volume that we need to dilute. All right? And then to prepare 625 mils, well, if we're preparing something, that's going to be our final volume. That's what we end up with. So that will be V2. And then we're left with 2 percentages as concentrations. One is 25%, and one is 4.25%. And so when we compare these two values, 25 obviously is a bigger number than 4.25. So 25% goes to C1 and 4.25 goes to C2. So now we just fill these numbers into the equation. Okay? So it's 25% times V1, because that's what we're trying to figure out, is equal to 4.25% times 625 mils. So now we just need to solve for V1. And if you remember from algebra, we just divide both sides of the equation by 25%. And 25 divided by 25 on the left side is 1, and 1 times anything is that value. And so on the other side, we divide by 25%, and now we actually have to work through the numbers. All right, and so we put this into the calculator. We come up with 106.25 mils. But of course, we need to be mindful of significant figures. And so after we adjust for significant figures, we have 3 significant figures, and that's our final answer. Okay, so that means that we would take 106 mils of 25% stock solution and dilute it to a final volume of 625 mils. So we would have to add enough diluent, right, ultra-pure water. We'd have to add additional ultra-pure water so that when we take this 106 mils, we add enough water so that the final volume is 625 mils. Okay, are you ready? Let's do another one. Here we go. Determine the concentration of a solution prepared by diluting 15.0 mils of a 2.0 molar sodium chloride solution to 20 liters with ultra-pure water. All right. So again, we just anchor ourselves by writing down the main equation. C1V1 equals C2V2. All right. And now we need to figure out what the numbers in the problem correspond to in the equation. So again, we read carefully. So it says solution prepared by, right? Concentration of a solution prepared by diluting. So we don't know what we've prepared. We don't know the concentration of what we have prepared. So that's C2. All right. And then by diluting 15 mils of a 2.0 molar, so this by diluting, this must mean this is what we're starting with, to 20 liters as a final volume. Okay, so those are our other 3 values. We have now the 3 numbers, right? And we said we needed 3 of the 4 to do the calculation. And so again, C1 is 2.0 molar, and the final volume, right, because that's what we're trying to prepare, prepared by diluting to 20 liters, that's going to be V2. But now you notice, right, that these are not the same unit. V1 and V2 are not the same unit. So in this case, we're going to convert the 15 mils to liters. I just did that arbitrarily. You could have converted liters to milliliters, but I just preferred to convert milliliters into liters. So now we've converted V1 into liters. We're going to plug this into the equation, right? 2.0 molar times 0.0150 liters is equal to C2 times 20 liters. And again, we need to solve this equation for C2. So we divide both sides by 20 liters. And that leaves us with this, right? 2.0 molar times 0.0150 liters divided by 20 liters. We solve for that, and we get 0.0015 molar. And this is the correct answer. It's fine. We're limited to our 2 significant figures, right? Because here we only have 2.0 molar. But when you look at this number, a lot of times people want to make this into sort of a simpler numerical value. Instead of having 0.0051 molar, as you get used to working with these numbers, you may say, oh, I could make this easily into a millimolar concentration. And so in units of millimolar, we're going to multiply our 0.0015 molar times 1,000 millimolar per 1 molar. And now we have 1.5 millimolar. And again, this answer, 0.0015 molar, is absolutely correct. But in some cases, the problem or in the SOP may request the value in millimolar, and that's how you do it. Okay? All right. Hopefully you guys are following along. Let's do another one. what is the starting concentration needed to prepare 750 mils of 8.0 milligram per mil BSA using a 10 mil volume of BSA stock solution? So again, we're going to write down our equation, C1V1 equals C2V2, and we know that's the right formula to use because we have two volumes and a concentration. And I'm not going to use the arrows to point everything out from here on. Hopefully you're starting to see it yourself with our third example. So we need to identify the corresponding values for C1, V1, C2, V2. So here we go. It says, what is the starting concentration? So starting means initial, the first concentration. So we're trying to figure out what C1 is, all right? We're going to prepare 750 mils, so we're ending up with 750 mils of 8.0 milligrams per mil. So 750 mils, 8.0 milligrams per mil, these are coupled in the same sentence. So C2 is going to be 8.0 milligrams per mil. So again, now we're just going to plug this value into our C1V1 equals C2V2. We need to solve for C1, which again, then we're going to divide by 10, both sides of the equation by 10. Here's our expression. Plug this into the calculator, and we come up with our answer of 600 milligrams per mil. Okay, and so this is a little tricky because when you go through my measurement, or if you've already gone through it, the measurement significant figures and data analysis, we know that these zeros can be ambiguous, all right? But from reading the problem, and if we were in a laboratory situation, we would know that this has two significant figures, this has 4, this has 3, so our answer is 2, but in the lab, you really wouldn't write this as 6.0 times 10 squared milligrams per mil. You might have to do that on a test or exam in order to illustrate that you know the proper number of significant figures, okay? But before we move on, I want to make a practical point here, and that is 600 milligrams of BSA in 1 mil is a lot of BSA. That's 0.6 grams of BSA in 1 mil. And so while theoretically this is the correct answer, practically when you go into the lab and try to make up this stock solution, you may not be able to dissolve 0.6 grams or 600 milligrams of BSA in 1 mil. There's just not enough room. There's not enough water to dissolve the BSA. And so in that case, you would have to go back and reconsider the value. So, and probably what you would do is change the volume of BSA stock solution that you need to dilute. So you would make a less concentrated BSA stock solution, which would require a higher volume. Okay, and how would you know if you could actually dissolve 0.60 grams of BSA in 1 mil? Well, one thing you could do is look up on the internet the solubility of BSA, and so you could just do the search term solubility of BSA in water and see what happens. I didn't do that for this, but I just want you to have a little bit of practical consideration as you solve these problems. Okay, so let's do another example here. What volume of a 0.135 molar HEAPS stock solution is required to prepare 3.5 liters of 50 millimolar HEAPS? So HEAPS is a chemically synthesized buffer. And remember, the purpose of a buffer is to resist a change in pH. So buffers help to prevent the pH from changing. You can add a little bit of acid or a little bit of base, and the buffer kind of absorbs that acid or base, and the pH doesn't change. All right. There is a buffer capacity where if you add too much acid or base, the buffer will be overwhelmed and then the pH will change. But again, that's not our purpose here. I just trying to throw in some things to remind you that there's more to it than just doing a simple calculation. So HEAPS is a buffer. It's frequently used in cell culture. Okay, so let's look about how we prepare a working solution from a stock solution, even though I did not call the 50 millimolar HEAPS solution a working solution. So this is C1V1 equals C2V2 problem, we need to assign values to C1, V1, and C2 and V2. So what volume of a 0.135 molar heap stock solution is required to prepare 50 millimolars, right? So 0.135 molar is a larger value than 50 millimolar, right? So we're trying to solve to determine what volume, what V1 we need initially. And then C2 is going to be the smaller concentration, right? And V2 is going to be the volume that we want to prepare. So that was pretty easy. Prepare 3.5 liters. But we have a problem, and I've kind of solved this for you, but I will put up the conversions here on the side because we have molarity here and millimolar here. And remember, we said we can use this for any concentrations, but the concentrations must have the same value. Okay? And so here we're going to convert 50 millimolar into molarity, right? 50 millimolar times 1 molar per 1,000 millimolar. And for V2, I chose to convert this into milliliters because our measuring devices in the lab are calibrated in milliliters, and probably graduated cylinders or serological pipettes. So I just started by converting this into milliliters, knowing that's probably the unit I will need for making my measurement. Okay? All right. So we're going to plug the values into our C1 V1 equals C2 V2 equation, and this is what it looks like. And so we see that we need to solve for V2. I'm sorry, for V1. We need to solve for V1. And so V1 is 0.05 molar times 3,500 mils. And then we divide both sides by 0.135 molar. When you do the math on your calculator, you get this number, 1,296.2963 mils. That's a lot of digits. So just intuitively, you should be thinking that's too many significant figures. So we're going to adjust for significant figures, and if we round this up, this becomes 1,300 mils. And so even though this is a lot, in our lab, we actually have a 2-liter and 4-liter graduated cylinder, so I can measure it using that, or I may have to use, for example, a 500 mil graduated cylinder 3 times to make the measurement. Okay. But again, we're looking at this, and we're going to assume this is 2 significant figures. The 3.5 is 2 figures. It's 2 significant figures. 0.135 is 3 significant figures. And 50 millimolar could be 1 or 2 significant figures, but we're going to have to make the assumption that this is 2 significant figures. So 2 significant figures, 2 significant figures, 3 significant figures. Our answer can only have 2 significant figures. So again, if you needed to, this would be 1.3 times 10 to the third milliliters, or 1.3 liters. All right, let's shift now. Hopefully you understand how to calculate volumes and concentrations using C1 V1 equals C2 V2. Let's look at dilution ratios, because these frequently occur in microbiology and in cell culture. Okay, so dilutions often are expressed as ratios, right? So 1 to 10 or 1 to 50 dilution. So let's sort of look at what this means, right? For biotechnology, and often for microbiology, the first number is the initial volume, V1, and the second number is the final volume, V2. So examples for this would be if it's a 1 to 10 dilution, V1 is equal to 1, and V2 is equal to 10. For 1 to 50, V1 is 1, and V2 is 50. Okay? The diluent, again, refers to the solvent or solution used to make the dilution by increasing the volume. So in most cases, probably 90 to 99% of the people that I work with say that a 1 to 10 dilution is prepared by combining 1 volume of the concentrated solution with 9 volumes of the diluent solution. And we're just using the term volume here so that it doesn't matter what unit we're using. It could be 1 milliliter of concentrated solution with 9 milliliters of diluent, or it could be 1 liter of concentrated solution with 9 liters of diluent. All right, but we get the 9 by 10 minus 1. And then similarly for 1 to 50 dilution, it's 1 volume of the concentrated solution with 49 volumes of the diluent, right? So 1 mil of concentrated solution with 49 mils of the diluent of ultra-pure water, all right? That's the way that the overwhelming majority of scientists interpret dilution ratios. But in some rare cases, right, a 1 to 10 dilution is interpreted as 1 volume of concentrated plus 10 volumes of diluent, right? So the final volume in this interpretation of a 1 to 10 dilution, the final volume is 11. Which way to go and how to make the dilution should be specified in the SOP. It should say 1 mil plus 9 mils. It shouldn't really say make a 1 to 10 dilution. But in research labs, they often say make a 1 to 10 dilution or make a 1 to 50 dilution. Okay? So let's work a few problems here. Describe how you would prepare a 2 to 35 dilution. As we move through this series, in some cases, in some examples, I'm going to give you some weird numbers just to prove to you that even though things look strange, if you follow the stepwise pattern, the answer will be correct, right? So I have never known any scientist in my life to prepare a 2 to 35 dilution, but let's just look at how this works, okay? So it would be 2 volumes of concentrate and 33 volumes of diluent. So 2 mils of the concentrated solution, 33 mils of the dilution solution, right? The diluent, the ultra-pure water. This could go as microliters too. This could be 2 microliters of concentrate and 33 microliters of diluent. Okay, that was pretty easy. Now, this one's a little trickier, but not really, right? And I see people struggle with this all the time, but here's the trick to solving this kind of problem, right? So describe how you would prepare 50 mils of a 1 to 15 dilution. Okay? To solve this, I would actually use C1V1 equals C2V2, all right? So we look at this. We have 3 numbers here. We have a volume, and then we have a 1 to 15 dilution. So we can interpret this 1 to 15 up here as a volume, but we could also interpret it as a concentration because we know that we have 1 volume, so we can't have 3 total volumes. We need to have 1 volume and 2 concentrations. So I would treat the dilution factors as concentrations. Think of them as 1x and 15x, all right? And so we, again, always write our C1V1 equals C2V2. This grounds us. And then remember we said the larger concentration is always C1. The smaller concentration is C2. And so we're solving for V1, right? Because we want to prepare 50 mils. So prepare means this is our final volume. We just plug the numbers in, okay? And we have 15 times V1 equals 1 times 50. So we solve for V1, divide both sides by 15, and we get a value of 3.3 mils, assuming that this is 2 significant figures, okay? So, lots of people rationalize this out. They do it intuitively. That's absolutely fine. Remember, I said at the preference of segment 1, whatever works best for you. But this is a systematic way to do these types of calculations, especially if you have kind of weird numbers. So the way that you would carry this out in the lab is you would add 3.3 mils of the concentrated solution to 46.7 mils of diluent. And the 46.7 comes from taking the final volume and subtracting the volume of concentrate that we need to add to get the diluent. Okay? And that's our final answer. All right, now, let's just try this again. Slightly different units. Calculate and describe how you would prepare 80 microliters of a 1 to 20 dilution. Hopefully you guys are already ahead of me now and you're working through this, right? So again, I would use C1V1 equals C2V2. And we're going to treat the dilution factors as concentrations and calculate V1. So C1V1 equals C2V2. I know you're tired of hearing this, but repetition is the mother of skill. So C1 is 20, right? In our ratio here, 20 is greater than 1. C2 will be 1, and V2 is 80 microliters. And so we plug these values into our equation. 20 times V1 equals 1 times 80, right? Solve for V1, divide both sides of the equation by 20, and V1 is 4 microliters. Okay, the significant figures here are ambiguous because this could be 1 or 2 sig figs. But we're going to use 10 microliter pipettement to deliver this. All right, and so we will combine 4.0 microliters of concentrate with 76 microliters of diluent, right? Because 4 plus 76 gives us 80. Final volume, okay? All right, and so, the other way to look at this is we have our final volume, we have our volume of concentrate. So when we subtract the volume of concentrate from the final volume, that tells us how much diluent we need to add. All right, let's look at another one. What is the concentration of a solution after a 200 millimolar buffer was diluted 1 to 25? So now we're given the concentration, and the 1 to 25 are going to be interpreted as volumes. So again, C1V1 equals C2V2, but now we started with a concentration, so as needed, we can interpret this as a volume. So we write our C1V1 equals C2V2. C1, the concentration, is 200 millimolar, and we're asking what's the concentration after the dilution, so C2 is unknown, right? The larger volume is always V2, and the smaller volume is always V1. So we've assigned a value to each of the variables. Plug those in. 200 times 1 equals C2 times 25. Divide both sides of the equation by 25, and we end up with 8 millimolar. Okay? 4 significant figures, because 200.0 is 4 significant figures. These are ratios, so they are considered to have an infinite number of significant figures. All right, dilution factors. It's sort of a variation of a dilution ratio, but we do use the term dilution factors, and I want us to know what a dilution factor is and how we determine it. So a dilution factor is used to correct the concentration of a sample that has been diluted back to its original undiluted concentration. So a lot of times when we do assays and we're trying to determine the concentration of a specific molecule, also known as the analyte, so the analyte is the molecule that we're trying to determine the concentration of, sometimes we need to dilute our test solution in order to get the concentration into a range that is measurable by the instrument we are using. So if it's really concentrated, for example, spectrophotometers have a limited range of values at which they can detect changes in the absorbance. So we may need to dilute our solution to a smaller concentration in order to be within the range of the measuring device, right? So really this is just a dilution ratio. So maybe we had to dilute our original sample 1 to 30 in order to make the measurement. So in order to make the measurement, we decided that a 1 to 30 dilution would decrease the concentration enough to put it in the detectable, the measurable range. So the corrected concentration should always be greater than the uncorrected, that is the diluted value. Okay? So pay close attention to the wording or to what process was actually done in the lab in order to be able to arrive at the proper correction values. So diluted to means the final volume is already given to you. So I diluted to 200 microliters. The final volume is 200 microliters. Diluted with means I added diluent to my concentrated solution, and so I now need to add the volume of the concentrated solution plus the volume of what I diluted with. Okay? Dilution factors are expressed in the form V2, the final volume, the volume that you end up with, divided by V1, the volume of the concentrated, the initial solution. So when we're correcting for a dilution factor, the larger volume always goes on top, and the smaller volume is always in the denominator. Time for an example. What is the dilution factor when 20 microliters is diluted to 100 microliters? Right? So the 2 tells us that 100 microliters is our final volume. So the dilution factor is V2 over V1, 100 over 20. And if you do the simplification, this is 5 over 1. And so the dilution factor is written as 1 to 5. There are no significant figures here because these are ratios. When the dilution what is the dilution factor when 20 microliters is diluted with 100 microliters? So now we have with, and that means that we're actually combining the two. So the final volume is the 20 microliters we started with plus the 100 microliters we used to dilute the 20 microliters because it's with. So now our dilution factor is V2 over V1, 120 over 20, or 6 over 1 when we simplify that, or a 1 to 6 dilution. Okay? So let's try another one. Calculate the dilution factor when 15 microliters of a solution is diluted to 350 microliters. So hopefully you're thinking 2 means that's our final volume. 350 microliters is our final volume. So V1 is 15 microliters, V2 is 350. Dilution factor is V2 over V1, 350 divided by 15. 23.33 over 1. That's what happens when we simplify this. So that's kind of a weird number. So normally when you do dilutions and dilution ratios, you pick out easy whole numbers. But if you make a mistake, it still works. It still works. And that was really the point of showing you some of these unusual combinations. Calculate the dilution factor when 5 mils of a solution is diluted with 25 mils. So now we have the with, so we need to add the two together. Right? So the initial volume is 5.0. The final volume is 30, derived by adding the 5 mils we started with the 25 mils we used to dilute. So our dilution factor is 30 over 5, 6 over 1, or 1 to 6. Okay, now let's look at a correction because that's really what we need to get to the bottom line about, right? So after being diluted 1 to 9, the concentration of the protein solution was determined to be 5.73 milligrams per mil. So this is the concentration after the original solution has been diluted. So the original concentration is going to be higher, right? So calculate the original concentration of the undiluted protein. That is before it was ever diluted, and we know it has to be higher than 5.73. So again, this is really a C1V1 equals C2V2 problem because you're given a concentration, right? 5.73 milligrams per mil, and 2 volumes, 1 and 9. So C1V1 equals C2V2. Can't write this down enough, okay? C1 is what we're trying to find, right? That's the original concentration. V1 is the smaller volume, which is 1. C2 is the volume, is the concentration that we determined experimentally in our assay, right? Maybe we did a protein assay, Comassi Blue or BCA, all right? But C2 is what we determined the concentration to be of the diluted sample. And remember, we had to dilute it to get it within the measuring range of the instrument, right? And then 9 is the final volume because we diluted this 1 to 9. So to make the correction, this is C1 times 1 equals 5.73 milligrams per mil times 9. Divide both sides by 1 to solve for C1, and we end up with our initial, our starting concentration, our undiluted concentration of 51.57, but we only have 3 significant figures, so we're going to round this to 51.6. And that was our undiluted concentration of protein. Okay. Now, some of you who are watching this say you made that much more complicated. You could have just multiplied 5.73 by 9, and that's really kind of what I did, but I just showed you mathematically why you are allowed to do that, and it just makes sure that you don't get stuck when you do this, because oftentimes people use inverted dilution factors to correct, and then you get a smaller number than what you were supposed to get to start with. So just think about that. This is sort of more of a consistent way to solve this kind of problem. All right, next problem. 20 microliters of an unknown protein solution was diluted with 180 microliters of dilution buffer. Analysis of the diluted protein using the BCA assay indicated a concentration of 3.84 milligrams per mil. Determine the dilution factor and the original concentration of the undiluted protein. Okay, so the dilution factor, really, this is two problems. So we have 20 microliters, our starting volume, diluted with 180 microliters. So V1 is going to be 20 microliters. Our dilution factor V2 is going to be 20 microliters plus 180 microliters because we diluted with 180 microliters. So the dilution factor is V2 over V1, 200 over 20, 10 over 1, or a 1 to 10 dilution factor. All right, to calculate the concentration of the protein, again, this is a C1 V1 equals C2 V2 problem, but now I'm going to do this the way that experienced scientists think about doing a dilution factor correction, right? We're solving for C1, the initial concentration. So C1 is C2. That's the concentration that we found in the assay. This is the concentration of the diluted sample times V2 over V1, which is the dilution factor. Okay, so that's our dilution factor. So now we just say protein concentration C1 V1 equals C2 V2. We can plug this in to be consistent. And, we have C2 times V2 over C1. Here's C2, V2, and V1. And our final concentration is 38.4 milligrams per mil, right? So while people shortcut this, and it's fine to do that as long as you remember to put the larger value in the numerator, you're good to go. But if you consistently keep making mistakes, you can revert back to the C1 V1 equals C2 V2. Okay? And again, two significant figures because that's what is in our measured value. Three significant figures. Okay, we're getting to the end of this unit. Sorry for taking so long, but I wanted to make sure this was all consistent. So let's talk about stock solutions and how we prepare working solutions from stock solutions. This is really easy, but I just want to make sure we illustrate this. So again, a stock solution is a solution prepared at a much higher concentration than we will actually use or work with, all right? So we prepare this as a multiple of the concentration of the working solution, like 10x, 20x, 100x, whatever. So that x just means it's that much more concentrated than the working solution. So 10x, 10 times more concentrated than the working solution. 50x, 50 times more concentrated than the working solution. And as we said in segment 1, the advantages are this saves time. There's more reproducible preparation of the working solutions, and there's less storage space required, right? 10x means that if we had 1x bottles, there would be 10 1x bottles, but we only have 1 10x bottles. The disadvantage is if the stock solution is made incorrectly, all the subsequent working solutions are now incorrect. If degradation or contamination occurs, right, then everything is incorrect. And because the stock solutions are constantly being opened and closed, they may be on the shelf for a week, 2 weeks, a month, right? You need to monitor them. If you're really going to be diligent, you're going to monitor these routinely for contamination, especially microbial contamination. Stock solutions that have nutrients in them like phosphate, right, or glucose, things like that, they can support the growth of bacteria. So you really want to check for contamination, and you want to catch that before it's visible to your eyes. So you might want to do a microbial culture plate like trypticase soy agar. Okay. A working solution is a solution that will be used in the experiment or process that you're going to work with. And so this is prepared by diluting the stock solution. So, ready for a problem? Here we go. Calculate the volume of a 15x stock solution required to prepare 500 mils of a 1x working solution. So guess what? Another C1V1 equals C2V2 problem, right? And so in this case, the 15x and the 1x are our concentrations, and we have the volume of 500 mils. So again, we assign numerical values to each variable. C1 is 15x, C2 is 1x. V1 is what we're trying to determine because it's the volume of the concentrated solution, and V2 is what we want to prepare, 500 mils. So we plug these values into the equation, solve for V1, right? Divide both sides by 15x, and V1 is 33.3333 mils, or we're going to round this up to 33 mils, okay? And that means that we're going to take 33 mils of the 15x stock solution, dilute it to a final volume of 500 mils. So that means we need 467 mils of diluent. We need 467 mils of diluent. Okay, and that 467, of course, comes from 500 minus 33. Okay. I think we're getting to the end here. Calculate the volume of a 36.5x stock solution required to prepare 2.30 liters of a 2.75 working solution. And again, this is just, I'm giving you kind of weird numbers to just help you gain confidence in the process. And just if you follow the pattern of steps, you're going to get the right answer. So again, right, we have two concentrations and a volume. So this is going to be a C1V1 equals C2V2, right? The X's are really concentrations here. 36.5 is greater than 2.75, so C1 is 36.5, which means 2.75 has to be C2, and we want to prepare 2.3 liters, so to prepare means that V2 is 2.30 liters. So we substitute the numbers in for the variables. 36.5 times V1 equals 2.75 times 2.30 liters. We're going to solve for V1, divide both sides of the equation by 36.5x, and we get 0.1732876 liters, but none of our laboratory measuring devices are in liters, and that's too many significant figures. Each of these has 3 significant figures, so our final answer will be 3 significant figures, and we're going to convert liters to milliliters because that's the units that our graduated cylinders are in. Okay? Okay, and so to prepare this, we're going to use 173 mils of the 36.5x stock solution, diluted to a final volume of 2.30 liters, which means 2.30 minus 173 says that we're going to need 2,127 mils of diluent, right? 2.3 liters, which is 2,300 milliliters minus 173 milliliters, gives us 2,127 mils of required diluent. All right, I'm going to encourage you guys to pause this for a minute and see if you can work this out on your own. So I'm going to count to 10 so you have time to pause this, and then hopefully you have a piece of paper there, and you're going to work through this and see what you do. Okay, we're back. Here we go. Calculate the amount of tris and SDS needed to prepare 4.00 liters of a 12x stock solution. The working concentration of tris is 25.0 millimolar, and a STS is 2.5% by weight volume. So this is a two-component solution. And if you remember from our stepwise process, what we said was treat each component as if it is the only one in the solution. They're both going to end up being in that final 4-liter volume, but initially to do the calculation, we're going to treat each component one at a time. Okay, so I just like to start by labeling it, saying we have tris. The stock concentration of tris is 25 millimolar. We need to make it 12 times more concentrated. Great. So we're going to take that working concentration that they wanted, multiply it by 12 because we want it 12 times more concentrated. 25 times 12 is 300 millimolar. But if we're going to calculate an amount, we're going to need to convert this into molarity. And so now we're going to use our grams equals molarity times volume times molecular weight. We're going to plug the numbers in, right? Our 0.300 molar solution, this is our 12 times more concentrated solution than the working solution, times 4 liters, times the molecular weight of tris, 121.14, which we obtained by an internet search. We just searched what is the molecular weight of tris, right? And so this gives us 145 grams of tris. And again, 3 significant figures because we have 3 sig figs here and 3 sig figs here. So we do the tris, 3 sig figs. So we did tris all by itself, and now we do STS all by itself. The stock concentration of STS is 12.5%. Okay, we're going to multiply that by 12 to get the stock solution. So the working percentage is 2.50%. We're going to multiply that by 12x because that's our stock solution. And we end up with a 30% concentration for the stock solution. So to figure out how many mils of STS we need and grams, we're going to take 4,000 mils, right? That's our 4 liters. But we do percentages in milliliters. So it's going to be 4,000 mils times the 30%, right? And 30% is 30 grams per 100 mils, or we need 1,200 grams of STS, right? Which we're going to dissolve in 4 liters. So think about this. Again, we addressed this earlier with the BSA problem. We have to be sure that we can actually dissolve 1,200 grams of STS in 4 liters. So again, we'd have to look up what is the solubility of STS in water and determine if we can actually dissolve 1,200 grams of STS in the water. But now what would happen is you would weigh out. Suppose that you could dissolve 1,200 grams of STS in 4 liters. You would weigh out 1,200 grams of STS, add it to 4 liters. And then you would weigh out 145 grams of tris and add it into the same 4 liters and then dissolve them. And that would be your 12x stock solution containing tris and STS. So hopefully you did okay with that. This was a little more difficult, but we've combined some of the things that we've learned in our segment so far. And that is the end of segment 3.